Okay, so today we're going to spend our time mostly on kind of this third piece of information that we can get from the spectrum, which is the splitting patterns. I know we've talked about chemical shift and integration already. So let's take a look at some general things about this. So one of the most important things about splitting is to remember that this is a through bond process, and it only occurs between magnetically unique nuclei. Okay, so if two nuclei are equivalent to each other, then they will not couple with each other. Okay, we'll see different coupling through different numbers of bonds. So we could have one bond coupling, which would just be from a proton to the C13 carbon that it's attached to. We can have two bond coupling, which would be geminal coupling, so the coupling between two protons that are on the same carbon. All right, and this is what we see when we have diastereotopic CH2 groups. Three bond coupling, this is the more common one that you hear about or learn about in organic chemistry, and there are some longer range couplings as well. All right, so what we're going to do, we're going to look at the causes of coupling, we're going to look at different combinations of splitting patterns, we're going to look at coupling constants, and what are called second order effects. All right, so the way I think to think about coupling, at least in this, there's probably more complicated ways to think about it, but you know that each of the nuclei, because they have their spin, they have two different orientations like we've talked about, aligned with the magnetic field and opposed to the magnetic field. So if we were going to observe one of these two protons, so let's say we're going to observe the peak for this proton, we're going to look at the effects of the other proton on it. Okay, and so the adjacent proton over here, if the magnetic field is going in this direction, B can either be aligned with the magnetic field or it can be opposed. Okay, and these are for this proton here. When that proton is aligned with the magnetic field, it's going to add slightly to B0. Okay, and when it's opposed to the magnetic field, it's going to slightly subtract from B0, and from the B0 that influences the proton next door. Okay, so this one is aligned. So this causes the red proton causes H to feel slightly larger, what we call B effective. Okay, and this one is opposed. And so this causes H to feel slightly lower B effective. And because we know that the two populations of aligned and opposed are almost the same, right? There's just a very slight excess in the aligned one, that what we end up with is if this is the peak with no splitting, H here, if this was the chemical shift, then we get one that's split a little bit up. This is the one that's feeling a slightly larger magnetic field. And we have the one that's feeling slightly less. and so we end up with 2 lines. Right? So when we have a proton that has 1 proton on the adjacent carbon, it gets split into a doublet. All right? So when we look at this, so so this would be something like this. The actual chemical shift is in the middle where it was at the top. Right? So if we have a doublet like this in our spectrum and we measure these 2 frequencies, if we want to report the chemical shift, we report it right in the middle of them. Okay? All right, and so this starts off what is kind of referred to as the N+1 rule. Okay, so if we have N protons on adjacent carbons, then we add 1, and that's the number of peaks we get. Okay, so for N equivalent protons, and I guess it's not going to be only on adjacent carbons. Let's say that couple. We get N+1 peaks. Okay, so we had 1 proton next to it, N+1, 2, we get a doublet. All right? Okay, this one's going to have another H here. Okay, so let's look at 2 other cases here and how we can kind of diagram this out. So if, again, we're going to observe the one in red, and we're going to see the effect of the 2 blue protons now. So those 2 blue protons can, like before, could be opposed or aligned with the magnetic field, but now we have 2 combinations, right? So they can either both be aligned, if this is B0 going this way, or one can be aligned and one can be opposed, or they can go the other way, or they can both be...
Go down.
Yeah, I should have those the other way, shouldn't I? Oh, yeah.
Should be opposite.
Yeah. Those should be this way. Right, and these are going from low energy to high energy, right? So the 2 that are aligned are going to be lower in energy. The 2 combinations that has 1 in each direction, they should be right at the same place as the beginning chemical shift, right? And notice the other thing is that these are in a 1 to 2 to 1 ratio in the possible combinations. All right, and so in this case, we get 3 peaks then in a 1, oops, those should be more even, but the splitting should be even. In a 1 to 2 to 1 ratio. Okay, these distances between the peaks, we refer to these as J, and J is the coupling constant. And it's in hertz. Okay, and if we have 3 peaks like this is called a triplet. All right, let's go up 1 more. If we have 3 protons on the adjacent carbon, we're observing this one again. Then we just look at all the possible combinations. We can have the most stable one with all 3 aligned. Then we can have 1 opposed and 2 aligned. Or we can have like this, or like this, right? Or the next one would have two opposed and one aligned. Okay, or this, like this, like this, or like this, and this, and this, or all three opposed. I'm doing the same thing again. Like this, right? And these are in a 1 to 3 to 3 to 1 ratio. Okay, so for this, we should get 1 to 3 to 3 to 1 ratio. 1 to 3 to 3 to 1. And likewise, each of these distances should be the same. Okay? This is, of course, called a quartet. Okay, so you can describe these patterns, these simple patterns called the Pascal's triangle. And have you guys seen this before? Yeah, so the way it works, you just keep carrying the 1 to the outside, and if you have numbers going to the inside, you add them together. So this kind of shows us if we have a singlet, of course we only have 1, we have a doublet, it's 1 to 1, triplet 1 to 2 to 2 to 1, quartet 1 to 3 to 3 to 1, but it goes all the way down. You know, here for example, if we had a septet 1 to 6 to 15 to 20 to 15 to 6 to 1. Right? So you can figure any of them out in this way. Right? And this, over on the coupling pattern over here, it shows kind of where the chemical shift would be down the middle depending upon those patterns and whether there's one peak that ends up in the middle or whether we have to take an average. Okay? All right, so I moved that one out. So the size of the coupling constants, oh, this is a different order. Hopefully I didn't skip some of those. Here, just a second, let me. Oops. Oh, maybe I wasn't even recording all of that. Dang. Can't. There's an H there and there. Okay, so there's one H on one proton on carbon and two H's next door. All right, so we have a doublet for the two protons and a singlet for the, or a triplet for the other one. If they're far apart, AX2, we see a 1 to 2 to 1 ratio in the triplet and a 1 to 1 ratio in the doublet, just like we expected. As they come, the chemical shifts come closer together. Notice this starts to slant off, and this does as well. The inside peak is getting bigger. However, if we get them very close, look at they don't only slant off, but the patterns fall apart, right? We can't see necessarily a triplet and a doublet anymore, so it can become very complicated. And then as they all become equivalent, then it's just A3. Okay, so as the coupling constant, as the chemical shift difference becomes small between coupled protons, then we get these type of second order effects. Okay, so an important thing about this has to do with the difference in using different magnetic field strengths too. It has a big implication on this kind of thing. Excuse me. Let me add in one more. So let's just imagine here, because when the one thing is that the J value, the coupling constant, is independent of B0. Okay, we've seen how the chemical shift depends upon, in Hertz, depends upon the magnetic field, right? So chemical shift in Hertz depends on B0. You know, we do the delta scale, and that doesn't depend on Hertz, but the chemical shift in Hertz does. So let's say we're going to look at I'm going to draw out two different peaks here. So let's say at 200 megahertz, I'm just going to draw out part of this. So let's say this is at 0, 200, 400. So each one of these would be 1 parts per million. And let's say that, and this isn't going to be all accurate, but I'm just going to make a point here. Let's say we have a, 200 megahertz. What's going on here? We have a triplet like this, and we have another quartet that's overlapping it. Okay, we have two that are overlapping. If we go to, say, 600 hertz, then our same scale, this is still 0, but this is 600 and 1200, and the chemical shifts will stay the same in parts per million, but essentially there will be more difference between these multiplets in hertz. Or the other way to think about it is the size of the coupling constant. If you have a very low field, then the size of the coupling constant actually becomes reasonably large on this scale. But if we go down now, there's 600 hertz in here, and so the coupling constant size becomes very much smaller. So the result is that the peaks become much narrower, the multiplets in the relative scale. And so this would collapse down to having something like this with a triplet and a quartet like this. And so the coupling constant would be the same, but you'd have a larger chemical shift difference in hertz, even though the parts per million would still come out the same. So you get much better resolution of peaks. And because the chemical shift difference in hertz becomes greater, the second order effects are less, because that ratio of delta frequency, difference in chemical shift over difference in J value, becomes bigger. So this is a big advantage for going to a higher field magnet. Does everybody understand that?
That's why you don't use a 60 megahertz anymore.
Right. If you look at some of those old spectra, you know, it's like, yeah, the triplet or something takes up a half of a part per million or something, you know.
Just look like it now.
Yeah, right. All right, so I ran out of these notes we have over here. Oh, so these are just some examples of some different coupling patterns. And I don't know if I had planned on giving this kind of, I guess we'll just look at these So here's just nitropropane. And I think this is kind of the average thing for the ones in the middle. We can see the triplet for the methyl group, right? We see the triplet for the signal next to the nitro group. And even though the two CH2s are not equivalent, we see this 6-peak, multiplet or sextet for the CH2 in the middle, right? Because it's coupling to 2 protons on one side, 3 on the other side, so 5 plus 1, it gives it 6.
That wouldn't look like that, right? I mean, it'd probably look a little bit more gross. Usually
The one in the middle?
the sextuplet, yeah.
I don't know. It depends on how clean the sample is and everything. I can't remember if these are real spectra. I might have simulated them on a program. And so then the next one is just isopropanol, right? So here, you can't, it's kind of small though, so this would be a septet. But it's really hard to see the smallest outside peaks there. Maybe I was going to do this whole Popel notation on this, but so this one, I think they call this an AX6 because they have 2 spins far apart. We've got 1, this would be A, and these are far apart but X, and there's 6 protons over there. This one I think would be something like A2, and then there's 1 in the middle, so sometimes we use an M for something in the middle. M2 X3. I guess that looks kind of weird, but and then this is the kind of a standard ethyl group, right? So A2X3. Yeah, these are all beautiful looking. You always wish that you could get one looking that good.
No water peaks.
All right. Well, let's just stop here before we start to look at some of these other multiplets. But yeah, these are pretty clean too. And if you get something that looks as good as that, but we want to be able to pick out the patterns in here and see and go instead of from looking at a molecule and predicting its pattern, we want to be able to look at a pattern and gain structural information from that. All right? So I think we're getting to the point where we're about ready to start working some problems. So maybe by Thursday I'll try to come up with a problem set that you guys can start working on. Okay?